12:15. I hope that everyone is a little bit refreshed after this short break. And in afternoon session, we have three presenters. First one is Axel Nordin from Yale University in Sweden, from Lund. And he'll present us integrated design software for prosthetics covering. Axel, please, you can share your screen because I allow to every panelist to share it.
All right. Yeah, thank you for the introduction. I hope you can see my screen here now. All right. Yeah, I'm Axel Nordin. I'm a senior lecturer at Lund University at the Department for Design Sciences. And I'll be talking about a process, a software that we have developed as a part of a research project for a company based in Malmö in Sweden that deals mainly with prosthetic coverings for leg prosthetics. So I'll bring you through that in the next 30 minutes or so here. But first, an introduction about us and about me, what we do mainly. My background is within generative design and optimization mainly. My research background is how to handle complex geometry using different optimization methods, such as the genetic algorithm. But I also deal quite a bit with topology optimization, especially in conjunction with additive manufacturing and the various aspects and constraints that comes with. But today's topic is going to be on mass customization, and in particular regarding prosthetics or cosmetic coverings for prosthetics, as you are shown here on the pages. A little bit about our lab, since this is focusing on AM. We have a fairly fully fledged AM lab at Lund University. We have access to various equipment for laser melting of metals and laser sintering of polymers, extrusion-based processes, selective and stereolithography as well. And the type of research that we mainly do within additive manufacturing is focused on design for additive manufacturing, how to deal with the constraints regarding the method, especially for production rather than prototype work. But we also look into lightweighting through topology optimization and other optimization methods, various types of lattice structures, cellular structures, with special focus on flexible structures at the moment. We've done quite a bit of work within heat exchangers and conformal cooling for injection molding tools, for instance. And of course, mass customization for prosthesis, but also furniture and other applications for this technology. And then we'll also do some strange stuff like printing food and gluten-based printing as a sort of side project at the lab. But coming to the topic of today's area here, I'll just mention a few things about the prospects of mass customization in this context here. Now, of course, with mass production, the cost of products has gone way down, and it's made available many products to people that weren't before. But it also brings with it that a lot of the products that you can buy in the store today are, mass produced. They're identical. There's nothing unique about your car compared to someone else's, really. But the need to individualize or to have something that's unique to you doesn't go away just because we have mass production. People still want to customize their bike or want to build their own computer case or maybe hack their IKEA furniture. And of course, in terms of medical applications, there is a need, you can't get around the need that each and every product needs to be individualized or customized to the patient or the customer. And this isn't just a psychological need, you can also look at it from a business point of view. Many have reasoned that the old business models where you sell a lot of a few things will, to some extent, in certain niche areas, be replaced by selling a little of a lot of things. So to sell a lot of customized products rather. And this, of course, isn't something that's entirely new, and it's something that the big companies have certainly jumped on the wagon with. Everybody from Nike to Volvo and Apple have customization options for their products. But mainly there are very superficial customizations available. You can adapt the material perhaps, or the color, but you can't do much in terms of changing the shape or the main function of the product. So that's sort of the motivation behind looking into this field of research for us. Initially, we looked into production methods that were not additive in nature, but rather more traditional, although controlled by digital methods, of course, such as CNC cutting of wood, as you see in this example here. And this example is a mass customization tool that we developed, a software for building your own bookshelf, basically. So you can input needs such as what you need to store and the overall size that you want, and then you can do a little bit of adaptation of how it looks. And then the software automatically makes sure that it's actually possible to produce it, given the different production constraints that we have on it. And we've developed the similar softwares for more professional uses, like this tool for producing customized heat sinks for various designs or products that need heat sinks for removing heat from, for instance, integrated circuits. So the benefit is that you can customize it and tune it while still keeping in control the heat that the components experience, so to speak. So we can use this approach in many different settings, but the setting that I'm going to be focusing on here today is, of course, within the medical sector, and especially within these cosmetic coverings here that fit on top of regular leg prosthetics. So these are not load-bearing, they're rather there to cover the real functional part of the prosthetic. But it gives, of course, a certain look. It adds to the overall impression of the prosthesis. So instead of being ashamed of having a leg missing, for instance, it can be thought of as a fashion accessory or something like a tattoo that you're proud of showing off rather than being ashamed of having. So this is the team at Anatomic Studios. And this is a sample of some of the cosmetic coverings that were developed using the software that I'm about to cover here. The overall process looks like this from the customer point of view. It's a 4-step process. You select a design. There are a couple of different designs available. You add some information, and this can be measurements based on your existing prosthetic leg and your healthy leg if you're only partly amputated. But it can also be a 3D scan of a healthy leg or the prosthetic leg as well. And then based on your data and the design you choose, the team at Anatomic Studios use the software to adapt it to the requirements, and then it's 3D printed and sent and delivered to the customer. So we can compare this process to the more traditional way that's still used to a large extent, where the patient or customer first needs to get an appointment with a technician to get the remaining stump cast. You get a molding of it, then you can cast the fittings to the stump. You go in for test fittings, and there are adaptations done so the fit is perfect, doesn't give any sort of long-term friction or pressure points, etc. And this is a rather slow process, of course. There are revisits required, so you have to go back to the technician. And there's a lot of hands-on work needed by the technician. So this can take weeks to complete, meaning that, of course, this is a quite expensive product, and the resulting product isn't especially aesthetically pleasing either. It's got a rather clinical look to it in most cases. So this, of course, leads to people not maybe wanting to exactly show off their prosthetic leg. So the idea behind this initially, in the beginning, was that the process would look something like this, where the customer can send in leg measurements or scans. The software automatically adapts a covering to this. It trims and splits it into two parts, so it can easily be fit onto the existing prosthetic leg. And the customer can choose a pattern between different generated patterns here, or a static pattern. And then finally, the parts are sent off for 3D printing. And there are some requirements for such a design tool that were developed early on. Of course, it should be faster than the traditional method, but it should also be faster than designing such a covering manually in CAD. Because even if you're dealing with digital data and you're doing this in front of the computer rather than doing it with castings and so on, it is a fairly slow and laborious process. Maybe around a week if you want to do something from scratch. Another requirement was to create parametric solids rather than volumetric data or meshes, just to be able to have more design freedom with the end result. You can add fillets and you can warp the shape and so on more easily rather than doing it with a mesh. And of course, we want to be able to do this quickly for new customers based on existing data, or adapt these coverings to the same customer if they want new ones, or if they are in a growing phase, for instance, and want to adapt it. And then finally, obviously, the parts need to work with orthopedic requirements like accessing ports for pulling a vacuum, easy removal of these coverings to get access to the prosthesis itself. Reduced netting should be able to withstand casual use, etc. So based on this, we developed the main principle here of the software, that we should be able to reuse designs, want to be able to quickly fit to either measurements or scan data. In those cases, this exists. And being able to change quickly between different patterns that we'll come to later. And of course, being able to output AM, suitable data for producing the part in the end. All of this software has been developed in two commercial softwares, Rhinoceros 3D and Grasshopper 3D. And as you can see on this picture, Grasshopper 3D is a visual scripting plugin for Grasshopper, meaning that instead of writing code, you can also plug inputs and outputs into each other. And there's also a wealth of various plugins for geometry creation available online that you can buy or license, or they're open source. And this is the end result, just to give you a feeling for how the internals of a software like this might look. This doesn't really tell you much of the functionality. It just tells you a little bit about the complexity and the various functions. So we have an input section, we have some geometry creation sections, we have some sections where we create patterns, and then finally an output section with some final filtering and the post-processing of the geometry. But to walk you through the steps here, we have the main elements. Of course, we need to deal with input data. The next step is to loft the curves, create a surface from our input data, trim it and scale it based on the patient. So we need to do that in a good way so it actually fits with the individual. And then we want to apply a pattern to it, which in this case, we choose to do in 2 dimensions. So there is a separate step here to get the prosthetic coverings flat, apply a structure to it, and then to wrap it back onto the 3D surface. And this is one of the more important steps to get right in our experience. So I'll talk a little bit more about that later on. But the first step here is to input the data with 2 different options. Either you input these measurements here, So the circumference of the calf and the ankle and the outer ankle length to the lower part of the patella. And then you also have an option to input the size of your prosthetic foot, because these typically come in some fairly standardized sizes. So it's important that the bottom of the covering fits with the foot itself. So there aren't any overlaps or parts protruding, areas for clothes to snag on, and so on. And the second option here, or in combination with measurements, of course, we can get 3D scans from the customer. And this is typically done together with a technician at whatever orthopedic clinic that the patient uses. And this is, I guess, fairly standardized technology by now. And we want, most importantly, a scan of the prosthetic leg itself, just to be able to check the fit of the covering. But if there is a scan of a healthy leg, then that's also quite useful to check the overall fit and make sure that there is some sort of symmetry between the two. Next step here is really to create these surfaces that will be the basis for the coverings. And we do this based on an approach where we have a number of sections of the covering that we call loft curves. And then we sweep or loft a surface along these. And then we have a number of trim lines that we use to trim the part in the end. And then finally, we can apply this pattern to it. So the one of the major things here to get right and to do automatically, more or less, is of course to fit or to scale the covering to each individual patient. So based on the measurements or the data, we have a couple of different approaches. The most straightforward one is, of course, if the patient inputs these measurements, and then we can simply scale our loft curves, the diameter of the loft curves, based on these circumferences that we get from the input in the ordering portal. So if we input different measurements here, you can see that the bottom of this covering, for instance, changes in its diameter, while the rest of the trim lines and so on stay the same. But the other option here is really to use the scan data. And there, again, we have two different options. We can either use the existing curves and scale the size of them based on the measured circumference at different areas of the actual leg. And this way we preserve some of the design features of the curves that have been manually designed. So often wise, this gives a more designed look. And the other option is to simply copy these sections from the existing leg, the leg scan, and to more or less duplicate that, not to 100%, there is some smoothing done, but we get a very close fit to the existing leg here. That obviously has been mirrored to be able to get the correct geometry. And while using a leg scan like this might seem obvious and useful, it turns out that using the leg scan as a basis doesn't always generate that nice of a look. It doesn't look that natural and doesn't look especially aesthetically pleasing in all cases when we just replicate the leg scan. So often wise, it's better to do scaling and to add some sort of manual design work to it to get a more industrial design look to the final product. And then finally, or then in the next step here, we have the part where we want to flatten our surface that we have trimmed and lofted. And then we want to add pattern to this and then wrap it back onto the 3D geometry or the 3D surface in the end. And depending a little bit on how you do this flattening and wrapping, you can end up with more or less distortions and more or less waves and so on in the final pattern, because obviously this is a curved surface. It's a doubly curved surface, so it's there isn't any way to do this perfectly to wrap this onto a flat sheet. It's just like trying to get sections of a globe, for instance. There isn't any mathematically possible perfect way to do this, but there are, of course, better or worse ways of doing this projection. So for instance, the default way of doing this in the software generates, as you can see on these pictures here, a fairly wobbly and non-uniform scaling of these rectangles here. Ideally, we would want to have these rectangles or squares as uniform as possible to not have distortions in the pattern, and to also have them as straight as possible to be able to keep straight parts of the geometry straight rather than following the curve here. So I won't go into the details exactly of how this is done in all these cases, but there are better and worse alternatives here. If we just follow the surface exactly and create so-called UV shapes based on that, so the sort of X and Y directions of it, then we get a pattern that's quite straight, but we also get a densification of the pattern where the curvature of the surface is higher. So up here we have quite a large rectangle, whereas down here we have a smaller rectangle. They're more densely packed. And that's something that we want to avoid if we want to keep the scaling of the pattern the same, and if we want to keep the sizes of the walls in the pattern the same. So instead, we can use other approaches where, for instance, we re-trim the surface and we do some geometrical measurements on it to do the scaling, and align these curves with the center line of the covering. And this way, we can get a very uniform covering of these rectangles onto the covering. And this means that we get a better quality of the pattern in the end compared to the default way or the other sort of trivial way of creating these mappings here. And you can also see that there is quite a difference in how this shape looks like when it's flat. And then we come to the pattern generation itself, where we have a couple of different options. We can, of course, apply a static pattern that's simply line pattern that one inputs, but we can also generate various patterns that will be random or semi-random, depending on what the customer likes, in 2 dimensions. And then we also have an option of creating 3D patterns directly in 3 dimensions. So rather than projecting it flat, applying pattern, and then projecting it up again, we can do it directly in 3 dimensions. But this, in this case, requires volumetric modeling for these versions. So you'll see the difference here. So here are a couple of different alternatives. We have different patterns depending on what the customer likes, like a Voronoi pattern, a Delaunay pattern, or just a square pattern. Or a smooth pattern, a sort of pentagonal pattern in this case, where you can adjust angles and so on. And there are also various options for having see-through holes or areas where you can see through the pattern. And we have options for applying a more tri-dimensional pattern in this case, which of course results in quite sharp edges. So one can apply some mesh smoothing to this as well to round out any very sharp corners that might lead to stress concentrations or just a worse look overall aesthetically. On top of this, we have some more experimental generative shape generation methods that are done not using parametric CAD surfaces, but rather on a voxel-based or volumetric model. So here, instead of representing this geometry using surfaces or splines or solids, we are representing it using voxels. So we have, instead of pixels, we have voxels that represent where there should be material or shouldn't be material in 3 dimensions. And using this approach opens up for creating more complex shapes and using some rather interesting pattern generation technologies like veneerations or knitting, or in this case, actually using a growth algorithm that will try to expand the line that you see here onto the surface. So in each iteration of this growth algorithm, it will try to expand and growing length without overlapping with neighboring sections here or line segments. So in each iteration, the part will grow and you will get more and more densely packed structure in the end. Now, obviously, printing this as is here, you can see that we have basically a very long wobbly spring, so it wouldn't be structurally sound to do this. But if we apply this onto a base surface, for instance, then one can certainly see this as being an interesting alternative to have something that's definitely unique to each and every customer. And then finally, on top of that, we of course want to apply some post-processing steps that mainly deal with things like adding a logotype automatically, which previously was a time-consuming step to do this parametrically. But we also want to be able to add holes, for instance, to be able to access ports on the actual leg prosthetic parts, or add cutouts and so on. And the final step is also to add attachments to the leg, to the prosthetic coverings, so that we can attach it to the leg prosthetic itself. Usually there is a tube of a standardized diameter where we can fit these parts onto. And then once everything is finished in terms of the design work, the parts are exported and sent to the partner 3D printing company, where it's either multi-jet fusion or SLS as a production technology, a little bit depending on the design. And they also do all of the post-processing of the parts themselves, such as sanding, polishing, coloring, painting, and gluing in decals that should be, or ornaments of other materials in this case. So they do quite a lot of the high-end fashion part in this case. So sort of in the conclusion here, the design time, that was the major barrier to doing this sort of customized work, has been reduced from weeks for the traditional casting molding process to maybe around a week if you want to do this work digitally with a CAD model and scan data from scratch. To today, it's probably down to an hour or 2 or 3 to adapt an existing design to a new customer. Obviously, if it's a repeat customer, it's less, but typically it's something like 2 to 3 hours to run this process through. So there is still a bit of manual work to adapt these curves and to make sure that they don't collide with the existing leg prosthetic, for instance, and to overall just check the quality of the exported parts. And all this data is saved in a database, so it's easy to find repeat orders. There is a search algorithm that will look at the input measurements of a customer and then look for close matches in the database, and then generate the base geometry as a basis for doing the new geometry manually. So that is also quite efficient. And in the end, all of the surfaces, everything in the design is NURBS-based or parametrical surfaces and solids. So it's very easy to continue work with if one wants to add on details later on, rather than doing this in a fully mesh-based fashion, as was the initial version of the software and similar softwares. And this, of course, comes with some limitations and challenges, but I think overall it's worth having a parametric model in the end rather than using a fully mesh-based model. And this is not the case with these parametrical, the experimental volumetric models that uses voxels. So that's a continued work, perhaps, to look at that. But yeah, that's the basis for one application and one concrete industrial use case for mass customization and for additive manufacturing, and how it's actually been implemented in practice and how it's used today. They're running and taking orders, so it seems like it's working in practice as well. And I'd like to take the opportunity to answer any questions, and of course, wish you all a Merry Christmas and Happy New Year. Thank you.
Thank you, Axel, for very interesting information with very interesting models inside of your demonstration of how to produce covering for prosthetic. So maybe if there is one question in our question and answers section, there is no question, neither in chat. Okay, just maybe a comment. I saw some also very interesting designs for production of prosthetics, not only for covering. So it's also a very interesting area for application of additive manufacturing. I don't have information about the durability of those type of prosthetics, but probably they are comparable with traditionally produced. So this is only a presentation of covering in order to improve, I should say, self-confidence of the people who wears it. We have one question.
Yes, what is the cost of covering, and is it covered by insurance? And the cost for a base model is, I believe, around 600 euros, but they range up to maybe 1,300 euros, I think, for the more intricate designs, depending on the size of the patient, of course. And it is covered by insurance, and you can get this covered, at least, it depends on the country, obviously, and the legislation. But in Sweden, a large part of the cost is covered by the government, and it's the same, I believe, in Norway. But in other countries, it might be that the customer ends up paying for itself or through insurance. But one can argue that even though these might be a little bit more expensive than the traditional ones, it also adds to the quality of life for the patient, since it's something that they're proud of, that they can display, rather than these rather clinical looking coverings that one typically sees in this case.
Thank you, Axel, for answering, and thank you, Mr. Broats, for putting a question. I hope that Axel answered you. Maybe is there any other question? If not, Axel, thank you once again for your very interesting presentation. And now